what I want to talk about is another part in the electromagnetic e-machine design focus part. And I will speak about how one can bring the results from an electromagnetic simulation into other physical domains and into the system world. So we have seen already part of it already, but I hope I can clarify some aspects of it. Okay, so I guess Dan did a good job to introduce you to the challenges of electric machine. So we are dealing here in particular with an electric drivetrain from a traction application, which is often, I would say most often, integrated like the one you see here on the screen. So you have your gearbox, you have the machine, you have your housing, and when you look into thermal aspects and also in vibration aspects, which is important for acoustic questions and comfort of the passenger, it is clear that we somehow have to think of this as a combined system. So, however, true co-simulation is far too computationally expensive. So this is not what one typically does. And therefore, one have to think about what is exchanged when and in which format. And this is what the talk is all about. Okay, this slide you have already seen. So what in the middle, you see the drive design. Detailed design is where the machine comes from. It's typically from a CAD system. In our case, this is the experience platform. And on the left side, we see here the finite element domains or physical simulation domains. And I will touch on noise and vibration and thermal management, but the focus will clearly be the electromagnetic performance, because this is, so to say, the source of noise and also the source of heat. And this have to be investigated. However, this is not possible without other physical domains, obviously, than electromagnetic. And we definitely need the route through the system world to derive important quantities. Without its noise and vibration, it's just of limited predictive use. Okay, also something you have seen already. So the design challenge is typically solved in an optimization, and the optimization is done in two stages. Whereas the first one, we already see an example from Bilkis, is a huge, is an optimization completely done in 2Ds, 2D, not coupled. So you have structures and electromagnetic KPIs, but there is no exchange between them. Both is done in 2D, and the reason is it should be fast. So the design space should be quite big, many operating points, not operating points, many design points or possible designs have to be investigated. And one should want to find candidates, which goes then in the phase 2. Okay, how this is done and what are the goals? Okay, sure, the goal is you want to find good design candidates, and desired is here fast simulation time. This is the most important one. So we have two domains, as I have already said. We have structural domain, which takes care that the rotor is will withstand the centrifugal load when rotating at max speed. And you have a lot of KPIs in the electromagnetic domain. This is not what I want to focus on, since this is what Bilkis already showed you before. Okay, so then you need the tool to combine these two things. This is Process Composer in this case. It is similar to EyeSight, where also Bilkis showed you an example. But Process Composer is living on the 3D Experience platform, so it makes it easier to integrate simulation and CAD when using Process Composer. But under the hood, so the possibilities in terms of creating a design of experiments or optimization are quite similar between these two tools. And obviously, if you have a huge design space, you somehow have to dive into the the multitude of results and find the best candidate. And for this is also a dedicated tool on the platform called Results Analytics. Now, here's the screenshot shows a bit how it looks like with scatter plots, and you have a lot of different views to help you define what is the best compromise between the contradictory requirements you may have. Okay. So this was just briefly about phase one. The most part I want to speak about the phase two, because so now we have a good design candidate or maybe multiple design candidates, and we can afford to run all of them in the more, let's say, advanced physical analysis, which takes longer, needs more engineering time to set this all up. So therefore you don't do it for all of the designs. Okay, first step is we somehow have to take the behavior of the machine over the whole operating regime and transfer it into the system domain. And this is done via a functional mockup unit. Functional mockup unit is an open standard. It is under the umbrella of the FMI standard org. So it's many applications out there understand this format. And what we are doing is we take a 2D lossless finite element analysis, do simulation for the whole operating regime, and extract from this data a reduced order model in terms of DQ quantities. I come to it in a moment, what it means for some of you which are not so familiar with machines. And maybe additionally, the FMU is not just a lookup, it also contains the interpolation between the points. And this interpolation will take care that you have energy conservation, which is a quite important aspect of it, because you couple here with the electrical machine the electromagnetic domain with the mechanical domains. And obviously what you put as electric power in, you want to have as mechanical power out, and if you have some loss in between, this is not as it should be. So all it's contained is this one exchange format. So since we are speaking here about currents and flux linkages, so it is enough to understand the behavior of the machine, but when you want to study noise and vibration aspects, you definitely need more, because you need the excitation for each tooth separately. The force which is created in the air gap acts on the tip of the tooth, and from there it excites the structure and will potentially mitigate noise, or at least starts to vibrate. And this we want to investigate. This is optional, and I will show you in a moment how it all looks like in the CST interface. So I want to show you that it's really simple to create such an FMU. Okay, just to summarize, the FMU is a full description of the machine, whole operating regime, all harmonics inside, saturation included. It's working in the DQ frame. You can ask for lumped and tangential tooth forces, and it contains also the interpolation method. You are not relying on the system level tool to interpolate, but it's, as I said, it's included and it's energy conserving. And what it brings you, sure, the authoring takes some time, depending on the resolution and on your machine you have at hand. However, it is good scalable. So each operating point to simulate can be sent to a cluster, and then you can also author this FMU quite easily or quite fast. But what you win is at the end, you have a really fast model in the system domain. So running, being able to create controls or these things and run them in seconds instead of hours when you would do it full transient co-simulation with finite element. Okay, just for some of you which maybe are not so familiar with the DQ frame, I just want to give a brief understanding. So when you have a three-phase system, a three-phase sinusoidal system, and you look here on the plot on the right, on the left, sorry. So, and you have here UVW phasors, and look at the change in the amplitudes over time, and you sum it all up, vector summation, you find out that you have a current vector which is rotating in a plane. And when you co-rotate with your coordinate system, it means that the D and the Q component of this current is constant. And there is some beta angle between them, and beta is called the load angle. And why people are doing this? The reason is because then you can design controls with the same approaches you know from DC machines, because it's much easier to work with more or less DC components instead of three-phase sinusoidal components. So, however, rotating is one thing. You definitely also need a reference, and the reference is chosen like this. You see here on the right side. You have a motor and a generator regime. So in the motor regime, you have positive torque. In the generator regime, you have negative torque. And at D, with pure D current, you don't have an average torque. And actually, having this in mind, that you want to find your reference in such a way, then you have a proper definition of your load angle. Okay. Mathematical, just for you to have a picture of all this, three-phase sinusoidal things transfer with mathematical transformation. So it's actually a frequency dependent or time dependent rotation matrix. You can transform such things into a two-component DC view. D and Q component are constant. The zero component is zero. And this is almost true also when you have higher harmonics. So if you look at the phase voltage of a machine and you apply this transformation, you see that the averaged zero component is still zero. It oscillates a bit, but at really low level. And also the D and Q component are oscillating, but they are much more, let's say, easier to handle, and you can more think like in DC terms as you could do with these sinusoidal things. Okay, having said this, I want to show you what it means to design to create an FMU in CST. So first, you have to define a valid machine simulation setup, and this means in particular you need the geometry. You have to set up excitations. You have seen already here, I was going through the individual parts. So you need coils with a winding scheme. You need a rotation, was the next thing chosen here. Rotation means you have a cylinder just defined by a radius being exactly in the air gap. You need the material, most likely nonlinear. These are nonlinear temperature dependent material data. And the BH curve of rotor and stator steel, also nonlinear. So what else is needed? So you take care of proper mesh settings, which is quite easy because the air gap can be refined just by defining a local mesh property on the rotation. And the last thing, to make it faster, you need cylindrical subvolume, most likely. Because then you also only simulate a piece of a cake. So now, let me stop here for a moment. When you have designed so if you have a proper electromagnetic setup, as I have just shown, coils, have magnets, have motion, have symmetry conditions, and have mesh settings defined, then you switch to the schematic view of all this, and here you define so-called drive scenarios. The drive scenarios are, a collection of load points. Load points are defined by speed, by current magnitude, and by the load angle. This is why I introduced you the Decoux frame before. And we have we can now define different drive scenarios depending on what you want to see. So you add a drive scenario to a sequence. One sequence means one particular model you have at hand. And here is a particular drive scenario for ROM authoring. So I don't speak about the other one. You can answer questions if you want to see more here. But when it comes to the ROM creation, it's a quite simple GUI. You say up to which maximum current you want to extract it. What are the pole pair number? Typically is filled out automatically based on the subvolume settings you have defined. you define a speed, which doesn't mean anything because you simulate lossless. It's actually snapshots of magnetostatic analysis. You choose a grid type. It's typically DQ, so meaning you build a grid in D and Q current, and you choose, either do it accurately yourself, what is the grid, or choose one of the presets. Normal was it in this case. Set some simulation settings. For example, use a time symmetry, just simulate 1/6 of it, ask for the FMU in a particular format, and then, if you like, this is the optional point, what I mentioned before, you say, I want to have the lumped T's forces additionally to the behavior model. So now here it's also easy GUI to earn. You define the number of stator slots. Where is the radius of your stator T's? So typically a stator inner radius and the number of points. And maybe just going back a bit because I want to show you how it looks like, because you get a visual feedback. Now you see here on the right these 6 dots. So this gives you feedback that you define it at the right point. And these lumped forces are then periodically, they are periodic because we only simulate this piece of cake. And at the end, we have a reduced order model containing lumped forces. That's it. Now, you can also set up here the acceleration settings. I didn't go into the detail. And when you are done, it was a bit fast now, so it's not real time. But here we created an adaptive analysis so that our ROM has a particular accuracy we are asked for. And here you can visualize torque, LD, and LQ, just to give you a visual feedback how good is your ROM. But the most important thing happens, let's say, in the background. The FMU is exported for you, and this FMU is the reduced order model for the system level design, for now at least. Okay, now we have the behavior model. So we have done finite element analysis, get the behavior model, surrogate model. It all somehow means the same thing. So excuse me when I switched between these two wordings. But there is more you need to know about the machine when you design a control. And this is the operating regime. So based on the behavior of the machine and the given voltage, speed, and max current, you can derive the operating point the control most likely want to set. And so we see here the D and Q current as a function of speed and the average torque. And up to these dashed lines, you can run at the best possible point. This is what Bilkis showed you as the optimized load angle. So where you get most torque out of your current, MTPA, maximum torque per ampere. However, at the dashed line, there you reach the maximum voltage. So if we are speaking here about a machine typically used in a car, where you have some battery voltage and you cannot supply more current if you don't have enough voltage at the battery. So there will be some threshold. And then you go into the MTPV region, so maximum torque per voltage region, and there you see you have to lower the current. But these two maps are then encapsulated into another FMU. Let's call it operating regime FMU. So it is a translation of average torque and speed into the current the control should set to make the machine operate at this speed and this torque. And for this one, we have another, let's say, subsequent drive scenario. So it is the drive scenario called loss map. So again, we choose another drive scenario in our sequence. Press on OK. Press on OK, yeah. Okay. So choose now a drive scenario, loss map, as I said. So, and here you give the control ranges. So first we choose where are the ROM. So we choose the ROM authoring drive scenario we have defined before. We specify what the board net can offer. So maximum peak voltage, maximum peak current, what should be the maximum speed, and also numbers defining the resolution of the result. And here, additionally, we ask for an FMU. And only then we get this operating regime FMU. Otherwise, we get plots in CST to visualize things, but not something we can run in the system level analysis. Okay, and we can export the EMAC ROM for SIMPAC, but this is another story, so I come to it in a moment. This has another application than the FMUs for system level simulation. Okay, here we see the results we get. We get the operating points, we get power versus speed for a motor and generator regime. We get the maps you saw already on the slide. ID versus torque and speed, and IQ versus torque and speed. Just to name a few, you see there were even more results you can look into. Okay. Having this FMU, the simplest thing you can do in the system world is to rebuild what you typically do with an electromagnetic finite element analysis. So maybe do a little bit more. So you ask for a torque at a given speed. The operating regime FMU translated into the current, ID and IQ, and the behavior FMU generates the torque and the flux of the machine. And so the output of it is torque and flux, as also the electromagnetic analysis will give. And here we see the results. So we ask for average torque is blue line, 100 Newton meter. And you see that these FMU contains the ripples. So the red one is then the torque rippling around the 100 Newton meter average torque. And here we can check whether ID and IQ comes out correctly. But okay, if the torque is correct, then also this one should be correct. Okay, however, this was really a simple case, so it's not so much use in it. It's just for you to understand how you can work with the FMUs. So the real thing happens if you create controls for your machine in the system world. And here we have an example for the control. There are many things behind each of these blocks you see here. But important is that each one can accept the FMU as an input, so that you have a realistic setup of your machine. So the controller, which is a torque controller in this case, needs the operating point FMU. Then, with the knowledge of what current the controller should set when you request a current, the modulation method makes up the PWM signal. And it's really a Boolean signal. This says the color here. So this Boolean signal is then sent to the inverter. So the inverter does the switching, has losses. There are different kinds of inverters, average efficiency inverters, or maybe a real switched mode inverter. And the voltage is then driving the machine and drives some load. Okay, so what comes out of it or could be the current waveforms. And the current waveforms are important for, let me go back, especially for the phase 2.2, because the higher harmonics in the current lead to additional losses. And if you want to drive a thermal analysis, you need to have accurate loss description. Otherwise, it's you miss an important aspect of the whole analysis. So, and what you can do now is you take the operating points from the loss map drive scenario. Each dot represents a torque speed combination. The torque speed with this control circuit will drive the machine up to reach these operating conditions. But with since an inverter is included with the real switching, you get the phase currents. You see the higher harmonics, and the phase currents can be set back to a loss map drive scenario. And now you really have to do a finite element analysis to get such a loss map. So what you get, and you not only get a loss map, you also get losses into the different channels. Iron losses rotor, iron losses stator, eddy current losses, kappa losses, and so on. And you also get the loss distribution as a 2D volume heat source, or let's say surface heat source, what you can then hand over to the thermal analysis. And this is what was done here. So I don't go into the detail of the application. I'm not an expert in it. But you see here two types of commonly used cooling strategies for a drivetrain. Now we have here water jacket cooling, and on the right an oil spray cooling, where you cool down the hairpin. So losses from the hairpin, I come to it in the next talk, where I want to extract these effective effects in the overhang. Okay, now noise and vibration. We also use a reduced order model here, but it's a dedicated one. It's not open standard. We transfer directly from CST to SIMPAC to do something like this. So you have your parameterized geometry. Sure, maybe not the full. The full one is only needed in SIMPAC. Just the 2D section of the motor is in the electromagnetic part. It's in the yellow box. In this one, we extract with these two drive scenarios you have just seen, the ROM authoring and the loss map, the EMAC ROM. And the EMAC ROM is handed over to SIMPAC, and at the same time, Abacus generates a substructure of the whole device, and the substructure is also input for the multi-body analysis, so SIMPAC in this case. And these two things together then enable to simulate the surface vibration and also then the noise mitigation. Okay, what is inside of this EMAC ROM is actually a combination of the two FMUs I showed you before in detail. So we have the operating regime, we have the behavior model, but the crucial thing here is that the mechanical engineer sitting at the using SIMPAC don't have to know anything about the electromagnetic things happening in between. So he don't see current or flux linkage or something like this. He only see mechanical inputs and Lamt's forces he can use as excitation. And important, he has the whole operating regime at hand. So he can run any analysis he may want, tip in, tip out, acceleration, deacceleration, whatever he wants to do, he has the data at hand. And this is the strength of this reduced order model. Okay, with this I come to the summary. Actually, just a few pictures. So at the heart of what I told is the 2D electromagnetic analysis in CST using the machine task, and the machine task is able to extract the FMUs, what you use in the system domain, and the EMAC ROM, which you use in the multi-body domain.